thank you all for coming. This is the fourth NERSC Nobel lecture keynote talk, and we've had great attendance at all four, and this is actually setting a record. And each one we've streamed these online, and each one has had more and more online viewers as well. So the last one had 250. Given how many people are here, my guess is this will set our record. So I think if we had another few Nobel Prizes, we wouldn't. I don't know where we'd hold it. So it's a good thing. This is we only have 4 in the last 18 years. So I wanted to thank Professor Perlmutter. He's an astrophysicist at Berkeley Lab and a professor of physics at UC Berkeley, who is known worldwide for his groundbreaking contributions to improving our understanding of the evolution of the universe since the Big Bang. He heads the lab's supernova cosmology project, which in 1998 discovered that galaxies are receding from one another faster now than they were billions of years ago, a finding that led to a Nobel Prize in physics. Professor Perlmutter shared the 2011 Nobel Prize with Brian Schmidt and Adam Riess for their concurrent discovery that the universe is expanding at an accelerating rate, overturning the conventional notion that universe's expansion is slowing. Both teams reached this conclusion by observing distant exploding stars known as Type 1a supernova. These same research efforts garnered Professor Perlmutter and Riess the 2006 Shaw Prize in Astronomy, and Professor Perlmutter and Schmidt the 2007 Gruber Cosmology Prize. Over the years, Professor Perlmutter has received numerous additional awards, such as the 2002 E.O. Lawrence Award, the 2003 California Scientist of the Year Award, the 2005 John Scott Award, and in 2011, Professor Perlmutter and Riess were co-recipients of the Albert Einstein Medal. In addition to his work in the Supernova Cosmology Project, Professor Perlmutter is a lead investigator for the Supernova Acceleration Probe Project, which aims to build a satellite dedicated to finding and studying more supernova in the distant universe. He is also a participant in the Berkeley Earth Science Temperature Project, which aims to increase our understanding of global warming through improved analyses of climate data. So with that, I'll go ahead and turn it over to Professor Perlmutter. So I can hear.
Right, well, good afternoon. Oh, a little echoey. Should we turn down a tiny bit? Is it okay. So it's a pleasure to be here to help celebrate the 40th anniversary of NERSC. And when I was asked to give the talk, I immediately was starting to describe all the things that I thought would be fun to think about in terms of what happened with NERSC and what happened with the work we'd done. But then in discussion, we started realizing that, or I was told, that I had to assume that at least a large fraction of the audience wouldn't actually know what it was that the science that we did that led to the acceleration of the universe, how it was done. And so I was put in that slightly awkward position of realizing that in a home audience of this sort, many people will have heard me speak before, and yet many people won't. So what I thought I would try to take advantage of is the fact that I've been, over the years, arguing that the understanding of how it is that we understand that the universe is accelerating, how we manage to make that measurement, is something that you can explain very easily. And it's one of the few very fundamental aspects of science that I know of that you can explain easily. And so since I've been making the case that everybody should be in a position, in fact, I think anybody in the entire country should be in a position of being able to explain this at home to their family members. It's basically a bedtime story to your child. That I thought that for those of you who've heard it before, I would just give you a recap so that you would then be able to practice again, so you get this right, so when you come back. And for those who haven't heard it before, this will be your first round, and you can tell me whether it works tonight when you put your child to bed. Okay, so the story that I'm calling Data, Computation, and Fate of the Universe begins then with a quick recap of the Fate of the Universe part of the story, and then I'll move back to where we go from there. The story that you want to tell at night begins nicely enough with the idea that the very first humans must have found themselves asking these very deep questions when they looked out at the sky at night. And I've been saying that I think this is really what it means to be human, that you would find yourself looking at the stars and find yourself wondering whether it goes on forever spatially and whether it will last forever in time. And that the very deep fundamental question of that kind couldn't really be approached in many rigorous way until just this past century when Einstein put down his theory of general relativity, and he came up with concepts that allowed him to ask mathematically rigorous questions about the universe that we live in. He immediately ran into a problem. This is from the summer of 1917 when he started working on this, that the universe that he was calculating could either be collapsing in or it could be expanding out. And as far as he knew, and as far as everybody, scientists around him knew, we live in a static universe that wasn't changing. So he put in a fudge factor, something that most of us have been tempted to do at some point in our lives in a physics course. And when Einstein puts a fudge factor in, it sounds better than when most of us do it because he calls it the cosmological constant, and he gives it the Greek variable lambda, and it's all great, except it's not wonderful. It sort of makes a universe that kind of barely teeters on standing still. And it was only a dozen years later that he kicked himself, and he called it his greatest blunder for putting in that fudge factor, because that's when Hubble and colleagues measured did measurements and discovered that the universe really was expanding. And so we now believe that the universe that we live in is an expanding universe, and Einstein blew it. He could have seen this coming. Now, what you should at this point find your child saying to you at this moment when you're trying to explain this part of the story is that that's ridiculous. What do you mean that the universe is expanding? I thought the universe is everything. What could you be expanding into if the universe is expanding? And this is the obvious question that comes to in everybody's minds. So this next part of the story is going to be the crucial part whenever you explain to anybody, which is the part that I'd say 3/4 of the questions they ask you afterwards will all come back to the same point, which is that the universe that we're imagining here isn't a universe that is somehow a real explosion that's expanding into something else. You're supposed to use the somewhat, let me try the simplest version of the story. Now, it's still mind-boggling, but it's as simple as I think you can start with. And this is an idea that we live perhaps today, in an infinite universe. And you then have this problem that you can't draw an infinite universe, so you're supposed to imagine that these are all galaxies, but that now they go on forever up and down and into the screen and out to you, and it's just an infinite universe. It goes on and on forever. That's already kind of mind-boggling, I agree, at least though it's consistent. It's not, you're not saying weird things about things going, exploding into some space that is not universe. So that's okay. So you have an infinite universe. Then comes the big trick, which is that when you say the universe is expanding, all you really mean is that all the distances between the average distance between those galaxies, it just gets a little bit bigger. And that's all we mean by an expanding universe. So it could be infinite now, it could be infinite in the future. The only difference is that there's a little bit more distance between every galaxy. And so when the universe expands, it doesn't expand into anything. If anything, you're sort of just puffing extra space in between the galaxies. And so, all right, it's still bizarre, but at least it's consistent. And that's and if you can get that picture into your family member's mind, that's the one that I think will help understand the rest of the discussion. So now you have something different to be thinking about, and Einstein now gave us a different picture at this stage, which is that now you're imagining a universe that's actually changing in time, and so you find yourself asking things like, well, if it's expanding, is it going to keep on expanding? And wouldn't all the gravity of attraction between all these different galaxies, wouldn't that sort of slow the expansion? And that's something that you can now actually take that, what seemed like a very philosophical question, you can now take it and make it a practical measurement question, because you can now say, well, why don't we go look back into the past and see how much the universe was slowing down before, and that might give us a hint as to what it's going to do in the future. To look into the past, though, is something that astronomers are really good at, and I'll show you why. And this actually began this particular work began in the 1980s when it was realized that there was a particular kind of exploding star, a particular type 1a supernova. When a star explodes in a distant galaxy, it can be tremendously bright. And these type 1as can be brighter than the entire galaxy of, 100 billion stars that they explode in. Now, not for long. They just brighten in a few weeks, and they fade away in a few months. But for just that peak brightness, they can be brighter than the entire galaxy of stars that they're seen in. That means that you can see them very far away. And if you can see something very far away, that means, in astronomy, that means that you're actually seeing farther back in time. So here, when you're explaining this, I think you'll find that most of the people you're talking to, but maybe not your youngest children, will be aware that light takes time to travel. And even the ones who are aware that light takes time to travel, though, probably haven't really thought about how long it takes to travel across distances that you get to see in astronomical observations. So here you should start pointing out that the light from the sun has been traveling to us for 8 minutes. And so you can say to them that if the sun were to go out, there'd be no problem for 8 minutes. The nearest star is more interesting. We are orbiting around the sun 4 times while that light is traveling to us from that star. So we're not seeing it right now. We're seeing it as it was 4 orbits around the sun ago for us, 4 years ago. But then once you get to the nearest galaxy of stars, now you're seeing this light from this galaxy that you look as if you're seeing it today, but really you're seeing light that left 150,000 years ago. So here on Earth, when that light left, that's when we had the first evidence of human culture here on Earth. And that's still nothing compared to the nearest congregation of clusters of, clusters of galaxies. So if you look at groups of galaxies altogether, the nearest one of those clusters of galaxies is far enough away that that light that you see here in this image, these are galaxies here in this image, not stars. And the light from these has been traveling to us for 65 million years. So at the time when this light left that location, we're seeing what it was like then when here on Earth the dinosaurs went extinct. Okay, my extinct dinosaur, right. So, but still, that's still nothing compared to how far away you can see with these very, very bright supernovae. The furthest supernova that we are seeing these days, the light has left this point some 10 billion years ago. And that's, I think, an amazing story to tell people, because you can point out to them that there's just a bit of history. It lasted for just a couple of weeks as this thing brightened, and then a couple of months as it faded away. And then that photon started traveling to us from that very distant galaxy. And while it traveled to us, we had to take this bit of dust that was here and congregate it into a solar system. There was no solar system at that time. The stars, the sun had to form out of that. The planets had to form. We had to start some primordial soup going so that you could get some single-cell organisms. They had to evolve to basically eventually get out of the water and onto land. We had to evolve. We had to figure out how to build telescopes. We had to build a really, really big telescope. In fact, the particular one that we needed to observe that was designed to one flight up here, the Keck telescope. And then we had to go construct it, get it all tuned up, and then swing it over and point it just in time for that photon to come in 10 billion years later and catch it on this, on your detector. So it's really just in time work, to. So 10 billion years later, we now get to see a tiny bit of history from that period, which I just think is just a great story to be able to tell. But this is really actually very useful, because now we wanted to know about how the history of the expansion of the universe will tell us about the eventual fate of the universe. What has it been doing, and what will that predict for what comes up? So what we want to use then is the fact that these supernovae not only can be seen very far away, but you can even tell how far away they are, because the particular kind of supernova we're describing, these type 1As, always brighten to the same brightness and then start to fade away. And so approximately the same brightness. And so you can treat them a little bit as what an astronomer calls a standard candle. The further away you go with a standard candle, if you walked across the room, the fainter it would look. And you can just measure how far away somebody had gotten by how bright that candle appeared. Similarly, the supernova, you can tell how far away it is by how bright it is. And then you know how long it takes for the light to reach us, because you know the speed of light. So every individual supernova just tells you, just by its brightness at its peak, how far back in time that particular explosion occurred. And now that's really convenient. But there's one other thing you'd like to know about that particular moment in time. You'd like to know how much has the universe expanded since that time. And the supernova, once again, managed to tell you that, because the light from a supernova, if you're able to stand right next to it and not die, it would look mostly blue. So that's a short wavelength of light. Then that light has to travel through the universe, but the universe is stretching while it travels. And in an expanding universe, as I was just describing to you, anything that's not nailed down stretches just with the universe. And that includes that very photon of light. So by the time it reaches us, it looks much redder. And you can just read off from that red shift, as we call it, how much the universe has stretched since that particular date when that particular supernova exploded. So that is really convenient. You get this amazing trick that the redshift is just allowing you to read off the stretch of the universe since any individual supernova explosion. And if you put this together then, and as you tell the story, you can say, OK, so in some distant galaxy over here, a supernova explodes. It looks blue. It starts to travel to us in an expanding universe. And while it travels, it gets redder and redder, just as the universe stretches, until it reaches us. And you read off by how red it looks exactly how much the universe has stretched. And that's the entire story you need to tell. And then your child can go to sleep. And okay, so, but they may want to know what we did with that and how how it all came out in the end. What was the answer to the story? So the story at this point becomes just a little bit harder to actually do in fact than it sounds like in that nice cartoon, because now what you really want to do is you want to find a whole series of supernova representing different moments in history. So you find one supernova that's pretty faint. Maybe it's a billion years that the light's been traveling to us, and so it tells you how much the universe stretched from a billion years ago. You find another supernova that's fainter. So maybe the light's traveling to us for 4 billion years, and you can read off from it how much the universe has stretched since 4 billion years ago. Another one, maybe 7 billion years back. And you could plot out the history then of the expansion of the universe using the supernova if you can find those supernovae. And that was where we were back in the 1980s when we realized that you could do this in principle, but we had not yet figured out how to find these very distant supernovae. The problem partly is the fact that supernovae are a real pain in the neck to work with. They only explode a couple times per millennium. There's only so long you're going to have your grad students. They don't warn you ahead of time when they're going to explode. So and also once they explode, they brighten in a few weeks and they're gone. So if you need to use the largest telescopes, let me see if I have not here. Okay, if you need to use the largest telescopes in the world to observe something like this, you have to write proposals 6 months in advance, and so it really didn't work to write proposals, saying, I want the night of March the 3rd. You only get one night, if you propose, just in case the supernova explodes in the next couple hundred years. And so early on, then the main name of the game was trying to figure out how to turn this into a more systematic, manageable project. What we ended up doing was developing these optical systems that would allow us to take a fairly wide field of sky and observe it and bring it down to a small CCD chip. And for those of you who've wondered what that sort of round bit of glass is sitting in the front hall of this building, that was the original instrument that we built, the original optics that we built to take a wide field and bring it down onto a small CCD camera chip. If you do that, now you can get hundreds and then thousands of galaxies in a single night. And in an image like this, you should ignore all the beautiful bright things in the front, because what you're looking for now are supernovae exploding in these little faint blue specks in the background. These are all distant galaxies, all these little blue specks. And those are the things that we were going to try to find supernovae in. So the next job, clearly, finally now, brings me back to the topic of today, which is computing. Because clearly, this was not a job, once more, for even your most patient graduate student to look through those thousands of blue specks and try and find this little extra bit of light on top of the blue speck that represents the supernova explosion that you see in a later image. And so we ended up, over the years, developing many generations of computer software that would allow the computer to compare the images and then home in for us on this spot right over there, for example, where if you blow it up, you can see that this area is brighter than that one. So here's the galaxy without supernova. Here's the galaxy with supernova. And if you subtract this image from 3 weeks before from this image when the supernova was up, you get just the difference, which is the light from the supernova. So that was a lot of work in the early days to try and get to the point that we could have the computers go through these, what at the time was vast amount of data, and find the supernova within, ideally, a few hours of the observation. So then we could go follow it, because you need to remember to measure it as it brightened and faded to get that peak brightness that you were using as your standard candle. So this was done in around, well, we thought it was going to be a really hard project. We started thinking it was going to take us 3 years to do the whole thing and find a series of supernova. After 3 years, we hadn't found any supernova. After 4 or 5 years, we had our first supernova. 6 years long, I think we demonstrated that we could do this in a standardized way, and we started semester after semester applying for time and going to all the telescopes around the world, because we needed to use like 4 or 5 of them to get good quality measurements of these sorts. And eventually also using the Hubble Space Telescope, where you can see the light from in space allows you to pick out the supernova as that little white dot from the background galaxy, whereas in the ground they're all blurred together. And we, every semester then, we would start to bring in half a dozen to a dozen supernova of this kind, until in '97 we finally had enough supernova in hand that we were ready to make a plot of the fate of the universe, as we might imagine, the average distance between galaxies as a function of time. And we were rather excited. We had 42 supernova in hand. For those who've read The Hitchhiker's Guide to the Galaxy, that seemed an auspicious number. For those who didn't, you can ask your friends later. The options were just great, because one option would be that you would find that the universe was slowing but going on forever. That would look a little like this if you're lying on your back and you had telescopes for eyes, I guess. Now, the universe expands away from each other, away from you, but it slows and slows, but it keeps on going forever. So that was option one. Option two, the universe has enough mass in it, enough density, that it slows to a halt, and then it collapses. So that one is a little bit more exciting, because it begins the same. It slows and slows, just like the other one. But this one, it slows and then turns around, and it starts coming back in. And around this point, you start getting nervous. And this universe comes to an end. And that was great. I mean, what could be better than to have a project where you go out, you just make the measurement of the brightness and spectra and colors of some little specks in the sky, and just doing that simple measurement, you get to find out, do we live in a universe that's going to come to an end? And so this was, it was the best project I could imagine. In fact, it was even better, because it turned out at that time, with this particular model of the universe we had, that if it did not come to an end, that meant that we were on one of these universes, which was a way of measuring that we live in an infinite universe. And some other, maybe if we have time for questions, I can explain what it would mean if we did not live in an infinite universe. But that was, I figured, what could be better? Either we measure that the universe is infinite, or we measure that the universe is going to come to an end. We were doing this just before the millennium, so we thought that we could walk around with a sign saying the universe is coming to an end or not, just in time. So it was really great. And then, of course, what happened was when we put the points on this plot, what we got was that, right? So that was the surprise that you've heard about, and that at the time really made us assume that we made some mistake, right? And so we spent a lot of time working on it. This means that the universe is not slowing down at all. It's going faster and faster. In fact, pretty soon, just whoosh, everything will be gone. You have to do all your astronomy now. I've been pointing out to the funding agencies. But it doesn't. They don't seem to care. So in a few billion years, you won't be able to see anything else. And the data, when you look at it on a real graph, with real error bars, looks like this. You have the nearby examples where the brightness of the supernova tells you how far away it is, and hence how far back in time you're looking. This is today, and you're looking back in time. The redshift, the blue ones, if there's no redshift, and then it gets redder and redder as you see more and more stretching as you go back in time compared to further back in time. And then, of course, the data that we found missed all the lines we expected. And apparently, we live in a universe that was decelerating for the first half of its life and then started accelerating for the last half of its life. And so that was what the actual data looked like at that time. Now, the conclusion of this story is, at this point, you have to tell your child, who I hope by now has sat up in bed, to listen to this part. You have to tell them that we do not know. Oh, and I should say that, by the way, this is a very good Berkeley story, because while we were analyzing our data up here at LBL, down on campus, at that point, we had now had a rival team, and they were racing with us. They were analyzing their data just at the same time, and we were seeing the surprise simultaneously. And of course, it wasn't just these two people. It was the group leader in Australia. It was the entire two international teams who were really struck by that. And that these were the teams that all came out to Sweden, to Stockholm in 2012. So that was a great example of a group project where the two groups together actually represented a very large fraction of the whole community that works on supernova. So it really ended up being a sort of community effort that led to this result, which I think is just a fun, a fun side of the story. Now, at this point, as I was saying, you have to admit cheerfully to your child who you're explaining this to that we have no idea why the universe is accelerating, because they will immediately ask why, of course. And the term we use, dark energy, is a term just to reflect the placeholder of what it would take in the form of an energy that would have to be spread throughout all of space that could explain an acceleration of this kind. And if it really is, in the end, this new form of energy that we haven't yet explored, then most of the stuff of the universe is made out of it, almost 3/4. So that's really striking. Now, it could be even, I know, more dramatic than that. I don't know if it's more dramatic. It may be that we haven't quite gotten Einstein's theory of general relativity right. Maybe there's some extra part in the story of gravity that we'll have to learn. And so now the race is on to try to understand this. Now, of course, the people who really lead this kind of race are the theorists. And the theorists have been at work hard ever since the discovery. In fact, since the original announcement back in '98, there's been an average of a paper published in a journal every 24 hours since that time. And they come up with great names for these theories. So I think everybody will love telling your friends that you're talking here about the phantom energy or the Big Rip cosmology, or if you can pronounce it, the ekperiodic universe. But it's also fair to say that none of these theorists will, at the moment, stand behind their theory. Now, not because they think there's anything wrong with what they wrote, but because they're trying to broaden the range of possibilities of what's going on, and really they say the ball's back in our court to help hone in on one or the other of these ranges of theories. And it's now the job of the experimentalists, the observers, to find out more about the properties of this acceleration, the properties of this dark energy, so that we have a fighting chance to understand what could be explaining it. People have not been just sitting around for the past, what is it now, 14 years. The supernova data has gotten dramatically better. So originally, this small sample of less than 50 supernova has now, well, here, let me turn this around and flip it upside down the way the astronomers like to look at it. It's now gotten to be over 700 supernova. Every one of these 700 supernova is better measured than any of those first 42 supernovas that I just mentioned to you. So there's been a tremendous advance in our understanding of this expansion history of the universe in that sense. However, it's fair to say that we still do not constrain the behavior of the dark energy in any way that really helps us. This is a plot of what we call the dark energy equation of state, which is, you can think of it as sort of the springiness of the dark energy in terms of how it wants the universe to accelerate, as a function of looking back in time for the higher redshifts. And really, it's only at very recent times that we have a very tight measurement at all. As soon as you get a little bit further back in time, these are very loose constraints, and they could conclude almost anything, including things that aren't dark energy at all. So we don't know much about what's causing the acceleration yet, in that sense. And if you ask, well, why not? 700 supernova, it sounds great. The answer is that the measurements that have to be much, much better in order to be able to get at the differences between the theories. So the current range of, so you can see the data has gone from this to something like this, but all theories are all within the thickness of this green line. So you need to be able to look for little changes of that history that are all hidden inside the thickness of that line. And so that means a factor of some 20 of improvement of the uncertainties in the measurement. Now, I think we have a fighting chance to do that because we now know a lot about all the steps that the light takes as it comes to us from the exploding supernova, and we know much more about the supernova themselves. And so we can, for example, the simulations that are done on, and this is once more tying back to where I'm going to get to with the NERSC and the computers. So these are supercomputer calculations done at NERSC where you can measure, actually let me see if I can get this to animate. So we have a, all right. Well, this is a nice animation, by the way, if you see it sometimes. You can see the, as you go deeper and deeper into the atmosphere of an exploding star, you can see the spectrum change. This is based on supercomputer calculations done here at NERSC. And so we have a very detailed story of what the different elements are and what's going on in the supernova that you can then use to match supernova at high redshift to low redshift if you can get very detailed spectra of the supernova at every different distance. And it looks now as if we have a fighting chance to get those kinds of detailed spectra because the mention of that satellite project that I actually was working on with many people here at the lab was originally called the SNAP satellite, Supernova Acceleration Probe. Over the years, that morphed into a project called JDAM, which was a joint dark energy mission that DOE and NASA was doing together, until eventually it morphed into a project that's now called WFIRST, which is Wide Field Infrared Survey Telescope. And I'm finally getting optimistic that we may have a chance that this is actually going to happen because it looks now as if all the stars are aligned. And we may actually get a chance to make this measurement, to have a telescope now that can make the measurements of the supernova that I showed you all the way out to some 10 billion years back, but with the kind of detail and precision that we've only seen in very, very nearby supernova up till now. So that is, I think, a very exciting opportunity for us to do that supernova measurement at that level of precision that we want. But it's not just supernova that we have as now over these last decade or so. We've developed a couple of other techniques. And so supernova takes you from the standard candle seen nearby, and you go backwards, back in time, by comparing more distant supernovas to more nearby ones. There's another technique now on the table that has actually made a measurement on this kind of plot, which is the baryon acoustic oscillation measurement that goes forward in time from the glow left over from the Big Bang, the cosmic microwave background. And I'll just say a word or two about that one because that's also something that's being led here at Berkeley, and it's also something that we use the computing facilities here to accomplish. If you look at that leftover glow from the Big Bang, you'll see there are sort of hotter spots and colder spots. The hotter spots represent places where things are more dense back in the very primordial soup days. And they represent spots that are where the density tells you where galaxies are eventually going to form. So if you then go forward in time and see where do the galaxies actually show up, the typical distance between the dense spots that you see in the cosmic microwave background blows up to be the typical distance between the galaxies in the expanded universe. So you now want to just measure the distances and the locations of each shell of galaxies as the universe expands, and it's another way of measuring that expansion history of the universe by going forward in time. Now, this is something that a team here at Berkeley has been leading a large international collaboration called BOSS, and they've now done these kinds of measurements at several different redshifts, and this is a level of precision that is striking. It's really amazing. So at redshift 0.57 and redshift 2.3, there are now measurements of what is the average distance, this typical distance between these overdense spots in the universe, and that leads us to points on this same expansion history, and those are shown here in green from this project BOSS. And the great thing about this technique is, well, first of all, it's the first time we've had something else besides supernova on a plot like this. But second of all, it's a technique that you can take much further. And so there's a project now that we're hoping is about to go ahead called DESI, Dark Energy Spectroscopic Instrument, which if you take seriously the data that you should be able to get from that project, those are these red points on this graph. And oh, actually, I don't have the blow up here in this one. And this has enough precision in it that you can trace amazing detail in the expansion history of the universe. So between the W1st doing the supernova at this high level of precision and DESI doing the BAO at this high level of precision, we really should have nailed the expansion history of the universe by the, well, now the DESI and the W1st are both expected that we'd have the data coming up in around the 2020s. So it's, you probably should not wait around this afternoon, but I'm hoping that within the not too distant future, we may actually have data that could tell us something about what are the properties of this dark energy. The question about also its being a change in gravity is something that you can also address using the other techniques of measuring where the galaxies are in space. And so that can be discussed. I'll get back to that some other time. All right. So I think what's interesting to point out here now in terms of today's context is that all of the story I've told you is amazingly computationally intensive. So the supernova work is, currently it takes on the order of about 1.5 terabytes per night that has to be processed. The next generation of these large telescopes that are being built to do the, both the ground-based one and space-based one I was telling you about, we'll be moving up to something more like 50 terabytes per night that you have to get through in time to be able to trigger on where the supernova are. We're using all sorts of data science techniques like machine learning, boosted decision trees, to be able to pull out these rare transients, these supernova, from the haystack of all the million candidates per night of things that look like they might change from one image to another. Then the supercomputer calculations then come back into simulating the supernova, so you can have a model to compare the supernova to and be able to make some extrapolations from what you're seeing. And you also need, and we've often used the computer centers at NERSC and that level of large-scale processing to do the statistical analysis of the cosmological parameters, because you have to mock up many copies of your experiment in order to get the statistics of what it is that you're seeing. Now, that's just the supernova. The baryon acoustic oscillation techniques also have been big users of the computing facilities. In this case, the imaging survey in 2025 is about 20 terabytes. We'd expect that in 2025, it'll be 60 petabytes. And once more, you need to do very sophisticated statistical analyses that do this Monte Carlos for the cross correlation of the millions of galaxies, so that you can collapse the problem to just these 2-point statistics on the sky of average distances. This depends, again, on comparisons to n-body simulations in how matter evolves in the universe. And so, once more, we're now looking at projects that are limited by how many particles you can mimic in a simulation. And the current state of art is these, sort of 2048 cubed to 4096 cubed. And in principle, we would like to see at least an order of magnitude more to get down to the scale that you'd like to be able to simulating to test these techniques that we're using that show where the galaxies evolve to. So these are clearly fields that are limited by what we can do with computing at any given moment. And of course, the cosmic microwave background itself, that is the basis for that technique that I was showing you, but also for much of our understanding of the fundamentals of the curvature of space itself. It's always been a matter of chasing the fainter and fainter measurements that you're trying to make. And each time, the data is growing exponentially. So back in 2000, they were working with 10 to the 9 samples. This recent Planck result is 10 to the 12 samples. And the next generation that's being planned would be something like 10 to the 15 that you need to be able to do this very complex cross-correlation of, once again, lots of Monte Carlos to understand the uncertainty quantification. So there's no question that we're seeing big data as the limiting element, and in general, data science as limiting element of this field. But it's not just cosmology. Of course, this is just one of many fields now where this is how we do our job. That's how we do our work. And I think it's interesting at this point to ask, given that we do downstairs here, and in Oakland, it's going to be moved to the new site very soon over here, have huge amounts of computing available, and we're getting good at what we do with it. You could ask what else is missing as we raise the ante and increase our power of our computing. And so here, I want to bring in another side of the story that is probably not quite so obvious when we talk about these problems. It's not just a question that we need faster computers and better algorithms to use them. There are these other aspects that just have to do with how humans and scientists work. And so I want to describe a few of these here. First, we have this problem that today, so much of what we do as scientists with computing is reinventing things. In every grad student who shows up, every scientist has to write code that, in many cases, is doing something that some other grad student or scientist has either somewhere else in the world been doing, or somewhere even in their own research group. The next person coming along ends up finding that it's easier just to rewrite something from scratch than it is to use what was there before. I think we need some way to not be working in this sort of morass of things that are hard to find and hard to build on. And so I think that it would make one of the huge advances in science will come when we figure out how better to make it possible to find already what's out there that you could build on, and to be able to be contributing and maintaining code that could be useful for a larger community. So if we figure out a way to do that, I think that will actually revolutionize science in a way that's not obvious until you think about how much time we're spending trying to reinvent things that other people have already worked on. And we have also not solved some of these sociological problems, that we don't have good ways for people who are really expert in the computing side of the world to have a career when the group that they would ordinarily go with, in other words, the scientific team that they would work with, would identify them more as a computer expert, whereas the computer scientist would identify them more as a, let's say, an astronomer. And so it's right now we're in this funny position where some of the people that we need most in the sciences have no natural home in the academic world that we live in. And of course, we have the more just simple problem that the training to do all these things is just sort of by hook or by crook. Often people learn their programming on the job as they need to, and I would say that most of us don't learn the best practices if we're scientists. This is clearly not the optimal way to be trying to do something where the whole field is limited by so much of the computing that we need to do. Some less obvious things is that I think it's not just the fault is not just in how we're training people. I think it's also in what it is that we're training them to use. The programming languages and environments, I think, are still aimed more at what you need if you're a programmer than what it is that you need if you're a scientist trying to deal with data and simulations. And I think that we could be developing much better environments to actually do the science in, so you're not distracted quite so much from the science you're trying to achieve, and that you're actually able to focus on what it is that the question is that you should be caring about next, not on, do I need an extra little curly bracket here on the left, in this particular case. Clearly, there are lots of places where the interest and needs of the domain scientists, the astronomers and the neurologists or the neuroscientists and the genetics person, could be answered with the real help of something that's an interest and need of the methodologists, the statisticians, the computer scientists. Often they really will have solved something that is needed by the scientist, but there's often a huge gap between what's ready coming out of the theoretical solution that a computer scientist has come up with and has demonstrated with one example, and what's really needed by the scientist to get the job done tomorrow. And we have to find ways to get all the parts in between built. And then finally, it seems like we shouldn't assume that we already know the answers. We should be trying to use some ethnography tools to really see what it is that we're doing, and where is it that we're stuck as scientists, and where is it that the connections aren't being made. And I think we could do much better by just a little bit of self-study as we do all this. So I think there's a lot of room for great gains. I mean, we could, one of the fun aspects is that there's the possibility that we bring people who have not yet been playing with data science to answer questions. But there's this other fun side that you can actually have the chance of talking to people across all sorts of fields around these topics, because so many people share similar problems nowadays in all ranges of science, that when you get them together in the room and you start talking about a computing problem that they're working on, they have actually a lot in common, and at times might even be able to help each other in a field where ordinarily they'd never get a chance to play. So, as a cosmologist, you might get a chance to do a little bit of, neuroscience, or vice versa. All right. So with all this in mind, there's been some real new initiatives going on here at Berkeley. I was very aware of this because we had started a data science initiative for cosmology inside the Berkeley Center for Cosmological Physics. This came from, we had a donor that gave us money for that. And then, just in this past year or so, there's been a large push from the Moore and Sloan Foundation that let Berkeley on campus start what we're calling the Berkeley Institute for Data Science. And this is now 3 universities were chosen, NYU, Berkeley, and UW, to try out this $37 million cross-institutional collaboration for 5 years to see what can be done about these exact problems that I was just describing to you. So there will be a center called BIDS, Berkeley Institute for Data Science, that will live right in the middle of campus in the big grand library in the central campus. So it's ideally going to be a meeting place for people to come and solve problems together. And we hope that it will have a very close tie to the new efforts in this direction, including the new building that's just appearing just downhill here, here at the lab. And it feels like it's just the obvious time for these to come together. The lab itself is doing a big push on this scientific data. And there's this new initiative up here, which is being described as a extreme data science facility. And the idea that we obviously at DOE in general, but the lab also in particular, we act as the home for so many different large data collection projects that then turn into large data analysis projects. That this is clearly a facility that is just crying out to be built. And so we're optimistic that this will be one of the main homes for this for DOE, and that we see it as a place where you can combine a lot of different elements all together in here up at the lab, but then also working closely with campus. All right, so let me leave time for questions. And, but I also want to tell just the last little bit of history. So concluding this part, I hope it's clear that it's just a really exciting time in cosmology, and that we're about to be ready to collect and simulate and analyze the next level of precision data. I haven't focused quite as much on the fact that everything I'm describing to you of all these next steps, I see as very likely to be leading us to the next surprises. I don't think we're finished with surprises in cosmology, and that's because cosmology is still a young field. Our first tries at an understanding of the universe have done amazingly well, but every time we make a measurement that is significantly more precise, significantly deeper, we're actually learning new surprises. So there's much more of the story I'm expecting that we'll still get to see in this next generation coming up. On the computing side, I want to say that's also a really exciting time, I think, for data sciences for science, and that we're ready now to start exploring some new approaches. And there's much more to the high-performance scientific computing than we've yet accomplished. So I'm very optimistic on this side as well. Now, as I was pulling all this story together, I was realizing that here at Berkeley, and particularly at NERSC, we've really got a chance to witness a lot of these changes occurring that I'm describing as both the cosmology, but also the way that we use computing. And I was reminded that the very beginning of our supernova project, when we first were working, we were just working along with our best computer we could, which was a PDP 1144 at that time. And I don't know how many people in the room will remember that if you were actually trying to handle things like images, that's a tough thing in those days. So we had these images from the CCDs, from the telescope, and if you're going to have images, it meant that your programming ended up being remarkably not fluent. Now you were using something that there was the dreaded overlay. So that meant that you couldn't fit your entire program and that in memory at one time, so you were constantly swapping in different parts of the program that were going to be able to fit into your computer at any given time. Now, this was really clumsy, and I see it as a metaphor for all these other clumsinesses that I'm describing today. And it was such a relief just a few years later when we now moved over to VAXes, because VAXes swap and do page the memory in and out for you, and you didn't actually have to sit there programming it. I mean, these are dumb things that that you never want to hear about. And yet, I'm really hoping that when we come back for the maybe the 50th, 60th anniversaries of NERSC, we'll be laughing similarly at some of the things that we're the contortions that we're doing in our programming today, in our scientific programming, that they were just not the right use for a scientist's time. Now, of course, things got much brighter in the I guess it was the end of '95 when Bill McCurdy showed up as the first the first swallow of the harbinger of spring, whatever it would be. The first person who arrived to bring NERSC to us at the time. And I remember when he showed up, I think in one of his first weeks here, I found him after the end of a work day when he was still in his office and I was still in my office. And I said to him, I think that this would be a really great thing if we could figure out a way to start using some of these computing facilities for some of these cosmology problems that we're working on. And in particular, for the supernova project, I could think of at least 3 things, 4 things, 5 things, where it would really, really make a difference if we could just had a little faster, computing and a little bigger facilities to do work. And he was encouraging, and of course, it's always dangerous to be encouraging if you're the director of anything, because I think within a matter of well, first I was going to say within just a matter of months or so afterwards, there were now started to be some new equipment showing up on the floor, and this really dramatic movie star image of Horst showing up, and so there was really something here. But I was going to say the mistake was to be encouraging, because within just a couple of months we had put in our first LDRD proposal. This was what they call a quick start proposal, because as they were moving NERSC in, they said, well, why don't we see whether LDRDs, these are for those who don't know the terminology, these are the seed money proposals that you can do it at Berkeley lab. And so we immediately put in a proposal, and what we asked for in this case was that we said, well, there's lots of things we'd like to try, but as just one experiment, let's try bringing a supernova modeler here. One of the few teams in the world that does supernova modeling, had a great young student coming out who could make who we'd love to have come as a postdoc. And so within just a matter of months afterwards, we had our first postdoc who was able to not only handle data, but also handle theory and for the supernova. And so now, I don't know if everybody knows, but Peter has just now been advanced to is it a what's the exact title called now? Does anyone remember? I know he's a CRD lead for data, or he's a division deputy. Division deputy. That's right. So you figure that's a pretty good start. And then we were very quickly using as much as we could of anything that was offered to us. That included analysis capabilities and, of course, this amazing storage capability, which I think it's worth using just so you can show the slide in your talks. It's gorgeous. And then you find surprising aspects of the fact that we now had a computing center here that made a huge difference. One of them was the fact that we got to the point where we were using telescopes all over the world and bringing data back here. And there was one night in particular I was remembering where the observers at the telescope were observing, and we were not getting the data back here. And I was trying to figure out what was going on. This is the very early days of the internet, by the way, that were going on. But at this point, we did have ESNet here. And so I ran downstairs to the control room that happened to be here. And I said, can you tell us what's going on? We haven't gotten any data for the last few hours. And we got to see and we have to finish the analysis tonight because there's another telescope online tomorrow night. We have to know what we have. So they did a little bit of hunting around and came to the conclusion that there was a rogue program at Brookhaven over here that was just dumping stuff onto the network and clogging the network, which apparently you could do at the time. So since we are all powerful here at Berkeley, the ESNet person said, OK, I'll just take Brookhaven offline. And instantly, our data started flowing through again And this is from the email from that night that we recently found. Our data started flowing through, again, at the tremendously normal 4 kilobytes per second speed. And we were back in business. But this gives you a sense of what it meant to us to have these computational facilities right here at the time. Of course, it wasn't just us. Similarly, at that same moment, the other parts of cosmology were really waking up to the need for computation here at NERSC. And so Julian Brill was hired just about that same time and was starting to work with this new boomerang maxima cosmic microwave background data, which then, within just a matter of a year or so after our result, was acted as our first confirmation that what we were seeing really was an acceleration of the universe. And within just a little while, you were seeing these kinds of things popping up all over the place. So, okay, I do need to stop. I do want to just leave a happy 40th anniversary NERSC and looking forward to the next decades in which we'll all get to do this again. But I hope with this and the new data science possibilities on campus that we'll really be doing this in this way that makes what we've done before seem archaic. Okay, thank you.
Thank you for a great talk. So we do have time for questions. I think this mic is pretty much dead. So I'll just ask you to speak up because there are people listening online, and then we're also recording so people can watch it later. So here's a question.
What do you think of the bicep results and the recent rumors that they didn't properly take into account the foreground noise?
So for those of you who, well, first of all, I'll repeat the question. What do we think about the bicep result? What do I think about the bicep result? So this is the bicep 2 collaboration. And I don't know whether everybody is aware that this was, it appeared in the front page of the New York Times because they were seeing what appeared to be the signals that you would expect to see from the very earliest primordial universe, even before the glow of the CMB. So it's a very exciting possibility that you can look back to that early time. There are a number of projects, both here at Berkeley and at other places around the world, that have been working steadily on going more and more sensitive and aiming to get to the sensitivity where you would see such primordial signals that would tell us something about the inflationary epoch of the universe. So it's a really exciting thing to start with. Now, the particular result is from an excellent team. They've made very sensitive detectors and built a great experiment. They saw it actually at a level of sensitivity that nobody expected that you would see it that easily. Everybody thought you have to go much, much further down. And it, of course, immediately made everybody start to look very closely at what it was that that their measurement consisted of. And at the moment, there's a lot of back and forth over the question of whether what we're seeing is really what they think it is or they hope it would be from the primordial time, or whether we're seeing some foreground noise that is not being properly subtracted out or not being completely subtracted out. And this is something I think that if you ask most people in the field today, they would say this is an easily answerable question, which we will know as soon as we get the results back from, for example, the upcoming Planck data release, which will be happening this fall. I would say that you have to call the jury out. You're saying the jury is still out at this moment. But it does focus your attention on what an exciting area that will be, assuming we can get to see those. And if we've seen it already, it's just going to be tremendous.
So I think this is working. So.
When you plotted your supernova, each point you had 2 axes. If you could add maybe a third or a fourth parameter to that, what would be your favorite parameter that we can, in this audience, understand that might help explain all those theories of what's going on with the acceleration process?
Well, these particular plots I'm showing you are just the history of the expansion of the universe. And so they would tell you if there's a property of space itself that makes the universe want to expand in different ways. But they won't tell you how to tell that apart from a change in theories of gravity. So if you were going to get another either axis on a plot, I'm not quite sure how you would do this, or at least another plot, you would like to plot how has material has stuff like galaxies and stars clumped over time in the universe, because that's very sensitive to whether you have the theory of gravity correct or not. So I think that would be the first thing that you would probably want to do. And the other experiments that we're doing are studying that clumping. And when I say we, I mean the cosmology community.
Let me get this one.
Hi. So I don't know if this is on or not, but when you first see the supernova results, the first thing you start thinking is, what else could explain this, right? So one possibility might be, say, a time evolution in what we call fundamental constants. But now, it's really exciting to have independent confirmation, like the BAO results and that sort of thing. And if they agree so precisely, can you now start to put limits on possible shifts in, say, the fine structure constant or the gravitational constant, that sort of thing?
Yeah, so maybe just to repeat in case it wasn't clear, the question is, if there's a possibility that the supernova could change as you go back in time, then that might be reflecting a change in some fundamental constants in the universe back then. Conversely, if we see that the assumption that we're seeing the same behavior back then as today is confirmed by, for example, the baryon-acoustic oscillation results, then can we put limits on how much of the change there is? The answer is yes, there are some papers that people have been trying out, and for certain purposes, it actually does provide a rather interesting constraint. I don't think it yet gives us a fine structure constant one that I've seen published that's better than the other ones, but I should check that again, because it's a good question. But absolutely. The other thing I was going to comment about that is that as you get these more and more precise measurements of spectra at great distances, you can make the constraints even tighter on individual supernova cases, because you can say this particular supernova out there has all the exact same evolution as it brightens and fades away. All the same things appear and disappear as this one over here. And that can be a very constraining story in terms of the physics has to be running very, very similarly there than here.
So I'm told that this is working for people online. So we do have one. So
Online
this
question.
is the age of social media.
Ah.
So we have a Facebook question. If circumstances permitted a round trip to any celestial body in the universe, where would you go?
Ooh. Wow. Well, I guess I'm a little bit practical. I think I would first try to go for ones that are not at greater than 10,000 degrees Fahrenheit and exploding. So I probably would not visit my favorite supernova. For my money, I would probably try to find one of these spots that looks as much like plants that we know as possible, because it really would be fun if we, eventually we could find some other life forms elsewhere in the universe. And it's probably the only kind of life form that we're going to recognize easily. So it's not necessarily that it's the best place for any kind of life form, but the kind that we would recognize, I think you probably want to look for in a place that looks a little bit like Earth. So maybe that would be my first stop. I hope we get lots of stops on this trip.
So you said in the beginning of the talk that initially the universe was decelerating, but it began to accelerate?
Yes. So one thing that's kind of interesting is that if you think about that simple model of the universe, where you puff extra space in between galaxies, and it's still infinite, but it just becomes more and more dilute because there's more space between every point. Now play it backwards and suck the space out, and things get closer and closer and closer together. But one thing that really cares about that is the force of gravity, because now things are closer to each other, and therefore the gravity becomes much, much more important. And as you get back to about halfway back to the beginning of the universe, you get to the point in which things were close enough to each other that gravity completely outweighed any other effect of this possible dark energy. So during that period, the universe did slow down for the first half of its life.
Okay.
I think we have another one. Oh, we have.
Could you just quickly describe DAISY and what's new about it?
Oh, DAISY, yes. So the project of measuring the expansion history using where are galaxies on average, what's the typical distance between galaxies at any given redshift, and then comparing that to the distance between the hot and cold spots in the cosmic microwave background, that project just depends on being able to locate where are all the galaxies. And so what you do is you can easily tell where a galaxy is if you can see it on a big telescope in the coordinates across the sky. What's harder is to get the distance, to get the redshift direction. There you actually need to get a spectrum of the galaxy. At least today, that's the method that you get the precision you need. And the way you do that is by actually trying to take lots and lots of galaxies all at the same time, put a fiber, a fiber optic fiber on each one on the focal plane of a telescope, and then bring that down to line them all up on a spectrograph. So now you can do thousands of galaxies spectra all at one time. The problem had been a very difficult manual problem. So a certain human was actually plugging hundreds and hundreds of fibers into a plug plate at the right positions that have been milled ahead of time where galaxies were going to be. And then you take that plate and you put it on a telescope. And that worked for this project called BOSS and for the previous Sloan Digital Sky Survey project. But when you want to get the scale that we're after and you want the numbers of galaxies you're after, that's probably not the way to go. So DESI is doing something similar, but with a robotic fiber positioner. So it has about 5,000 fibers, and then it just, you push a button, and the fibers all get sort of slightly rearranged to be where the galaxies will be, and then you observe. And then you push a button in your computer, and they rearrange again to where the next set of galaxies are as you move over on the sky. And that way, you can be much more efficient at getting many more thousands of galaxies positions. So that project is called DESI, and it's aimed at the moment, it's designed for the 4-meter Mail telescope on Kitt Peak that would then be taken over for this purpose.
I'm wondering whether you have considered ever the time-space deformation and how it can affect the results.
Say again, so the time-space?
Deformation or
Deformation.
pulsation of the time-space or whatever,
you mean whether
changes of the time-space.
Whether the time and space could be doing some sort of local deformations. Now, there's certain kinds of deformations that are just nowadays considered normal. So the fact that light bends because space can be thought of as being deformed as it goes as you're going around a very heavy object like a star. Or a galaxy, or a cluster of galaxies. That is something that is now just put into all the calculations, and we include that in as a matter of course. And so you have to average, your measurements over all the different kinds of effects that you infer of that kind. There's some error bars that come in because you don't necessarily know exactly which, massive stars or massive clusters or galaxies the rays of light have gone by. But that is part of the standard story. Now, there are other, among the huge number of, there's thousands of theories that I was showing you, those papers flying in. There are theories that try other kinds of deformation of space in rather unusual ways. So far, I'd say we don't have any strong evidence for particularly bizarre ones other, than the ones that we've already been putting in these calculations. But it's constantly being asked. I mean, people are always looking at different ways in which you could be having a theory where gravity would work in a different way to change the dynamics of the space-time that you're seeing.
I have a question about how do you tell the difference between redshift from an object that's accelerating away from you, like a light source, or redshift caused by the expansion of space-time itself?
The problem actually is one that, for certain parts of the measurement, is actually a serious problem that you can't tell apart just by observation. Particularly when they're nearby. So in the nearby expanding universe, the expansion hasn't had a chance to make that much of a difference, in terms of the redshift of things. So it's very comparable to the amount of Doppler shift that you get because galaxies are orbiting around us and around each other and locally. And so there, in the relatively nearby universe, now this is not nearby by any of our ordinary conventional standards, only nearby compared to the billions of light years that you're working with. But in that relatively nearby universe, you have to put in different models and try to fit what you expect this rotations and things to be. And it adds all sorts of uncertainties. The measurements I was showing you, though, are almost all well out beyond, so that the expansion of the universe is so much of a bigger effect than this little peculiar velocities, which are only on the order of a few hundreds of kilometers per second, then you can treat this as negligible for those problems.
So I have one question about your discovery story. So you mentioned before you spent 1 year to change your hypothesis, or say hypothesis of your experiment, yeah?
I'm sorry, you spent 1 year what?
At the beginning,
Yeah.
at the beginning of all your research,
Yeah.
you assume this is a slow down expansion, not accelerate.
Yes.
And then because you have many curves in that plot, so at that time, did you have the survey with all the curves? And then you have the data, yeah? You say, okay, now I change I have new discovery. So, and then the other question is, okay, let me repeat. So, because based on that figure, you have different surveys, like a slowdown or bigger crunch or this accelerated, yeah? And then you put the data in, and then you say, okay, now I got the new discovery, yeah?
Well, of course, at the time, right, most of the lines that we were considering were all lines that had different degrees of slowing. And it was when the data missed all those lines that we then started to take a little more seriously the fact that, well, we know about other lines that we could have put on, and then we started drawing the other lines that slowed and then accelerated. Is that part of the answer?
Yeah,
yeah,
that's
okay.
a part. And the other question is, did you feel the competition from the other group at that time during that year?
Yes, I mean, it was definitely this fierce rivalry. You know, we were racing at that point. Once we had gotten to the point where we were finding large numbers of distant supernova, the other team, which had been mostly at that point focusing on relatively nearby supernova studies, they joined in this game and they started trying to find these very distant supernova. And towards the end, they were finding them and we were finding them. We'd be passing each other at the telescopes because we have to use the same telescopes. There are only some telescopes in the world that could do the job. So we would we'd be heading out while they were coming in, or vice versa. Wave to each other at the airports. But generally people were doing this very much without telling each other what we were seeing most of the time. Now it is true that if anybody understood how difficult a project it was the guys on the other team. Guys and gals on the other team. And so there'd be times where, one of the teams would have a bad night. The telescope, the clouds would come in and would ruin a key night. That whole carefully timed sequence had to happen, or else everything would be wasted. And so there were times when we would trade with each other a night to help the other team, stay on target. Or there's one occasion where we took observations for the other team of one of the supernovae they had found, because otherwise it would get lost. And we got that data for them. But those were a little bit more the friendly exceptions to the fierce rule. And so at the time when we were coming up with these final results, we certainly did not know, and they didn't know that we were seeing these same sorts of things until we started announcing them at conferences.
My question is related to, we know that cosmic microwave background radiation was one of the sources of new information about the universe. Supernovas are another source. And I'm wondering now what astronomical objects or physical processes would be probably the next breakthrough in physics and our understanding of the universe.
There are several that are waiting in the wings that we think, so far now we have CMB, supernova, and I was talking about the baryon acoustic oscillation technique, this one that Boss and Desi do. But now the next ones that we're hoping have a chance include ones called weak gravitational lensing. And the idea is that distant galaxies, if you look at their light as it travels to us, it will get distorted in its path to us by the gravitational lensing effect of all the intervening matter between us and them. So that the more clumping there is in between us and the distant galaxy, the more you'll have bent the light and you'll have distorted that shape of the galaxy that you see in the distance. It's a very subtle distortion, so that any given galaxy, of course, has a weird shape anyway. So any one galaxy you never know. However, statistically, if you look at millions of galaxies, you can see this subtle distortion, and it can tell you where the mass is clumping in the universe, which helps make the plot that you were asking about before of what's the history of the clumping. That then tells us about the possibility that Einstein's theory of gravity needs modification. So that one, there's a new ground-based telescope that's being built called the Large Synaptic Survey Telescope, LSST. And that one we're expecting will be built and ready by the end of this decade. There's a new space based project called Euclid that the Europeans are making, which is aimed at that one as well. And then this WFIRST project I was talking about also is aimed at that. So that one I think has a real fighting chance that we'll at least get to try it, or we'll find out where the problems are with it as we do it. So that one is the first. And then people are also just trying to see where the clusters appear in the universe. So there are a number of projects now that are just trying to identify the clusters of galaxies. And the cluster ring itself is very much a test of the gravitational changes in theories of gravity. And so these cluster studies, for example, even this current project, the Dark Energy Survey, DES, is going to be finding very many clusters, and we hope making a systematic study of how those clusters evolve. But both those techniques, so far, we haven't yet been able to bring them online because there's a lot of systematic uncertainties that you have to figure out how to control if you're going to be able to use them. And so those are two very promising ones, but we're waiting to see them actually come into their full force.
So there's a whole universe of different challenges and problems that you and your team could have gone after addressing systematically. I imagine that along the way you ran into some pretty big hurdles with this one. Data that didn't make sense, models that weren't working, funding cycles, so on. So what convinced you to persist with this particular set of challenges as opposed to moving on to something else?
Yeah, no, it's a very good question, because this was a project that, at many moments looked like it was just not going to succeed. There were lots of times where we thought, and any ordinary funding cycle would have decided, okay, we tried that one for a few years, done. We were very fortunate, I think, in this case, that a national laboratory has the possibility of doing this longer-term, thinking and actually allowing something to proceed. In my particular case, we had Bob Kahn here, who is the division director, who was willing to hold off the pressures from Washington, saying, "Why are you doing that project?" And was able to let us pursue it. But your question also asks, why would we want to keep going when we went through 3 years without finding a supernova, and then 5 years we had one. That's not enough to make this measurement. And why would you keep going on it? And I think a lot of it had to do with the fact that it seemed like a really great question. The thing that you were getting to measure was one that seemed like, what could be better than measuring the fate of the universe and whether the universe is infinite or finite? I mean, it just seemed like that was a wonderful measurement to be able to get at. And the fact that it's at every moment while we were doing it, you could just sort of taste how close it was for us to be able to get there. That all you need to do was something that was very practical. It wasn't like you had to invent something dramatic. You just had to figure out how to get those little bright supernovae to be found, faint supernova, to be discovered and manage to get them into your telescopes and manage to be able to observe them enough. It just seemed like almost an organizational problem at any given stage. Now, of course, there were a lot of technical hurdles that we had to figure out along the way, and each step you learned more. But it did have that sense that this is, it's just, if we don't do it, somebody's got to do it. It had that feel.
So we'll just close with this. You probably get this question a lot. This is also from Facebook. It's from Diego Sandoval. As a physicist in training, what is your advice to someone like me?
Well, I think maybe the two themes maybe coming out of this talk here are very appropriate. One is from in the biggest picture, it's the answer to your question. If you can find problems and look for problems that you really would love to work on even when things go wrong, and that you would love to keep on working on even when the second thing goes wrong, and then after 4 years you would still love to work on it. If you can find that kind of problem, that's absolutely a wonderful thing to do. Now, that there's some luck. I felt really lucky when the time came that we had that problem to work on. Maybe you can find a problem that you just really enjoy the steps along the way, and that too is a big part of it. So that's the first most important one. And then, in my mind, the second one is just, given everything we've been saying today, just practically speaking, get really good on the computer.
Well, I think that's a great ending. So thank you very much.